Cześć, mam na imię Andrzej. Hello everyone, my name is Andrzej. I've been working at VPIphotonics as a photonics application engineer for 2.5 years now, and I have a fantastic time working on the photonic integrated circuits. Today, I would like to guide you through an interesting example of PAM-4 transmitter in our software, VPI Design Suite. It is the first in my little series of tutorials on how to design photonic integrated circuits using VPI Design Suite. We are going to design a circuit first, then we are performing a parameter sweep and an optimization of this design. The complete series is going to consist of 3 videos, not only because 3 is a lucky number and all good things comes in threes, but also because the 3 topics actually go together like 3 peas in a pod and they explore some closely related aspects of the software functionality. Right now, let us speak about a simple Mach-Zehnder modulator. It is based on 2 Y-couplers, 1 straight waveguide and 1 tunable electro-optic modulator. All these elements are included in the DemoFab PDK, which is our toolkit for designing photonic integrated circuits, and their characteristics are represented by geometrical parameters. Let's build our first setup. We need to put together 2 Y-couplers, a straight waveguide and an electro-optic modulator. There we go. The functional elements of our circuit are ready. However, to run a simulation, to characterize the circuit and to set up a proper test bench, we also need some additional building blocks. Fair enough. Let's get the work done. So we are adding an optical source, for example the module called Func Impulse Opt, and a signal analyzer. Another twist here is that by default the circuit simulation is performed in the time domain. However, we would like to run it in the frequency domain as we have no time-dependent elements in our circuit. I guess this approach represents the most accurate and fastest way of modeling passive circuits. So, how we do it here? Nice and easy. We can change the simulation domain by running one of the macros. Besides, we can select the option Create Virtual Galaxies to speed up our simulations and to resolve any possible deadlock issues. Are we ready? Let's run our schematic. There we go. We can observe the response of our unbalanced Mach-Zehnder interferometer. Let's change the theme of our schematic in VPI demo theme. For me, it is easier on the eyes. We can also change the name of our signal by changing the input name. After double-clicking on the trace, we can set the trace name, trace color and thickness. If you like what you see, it might be a good idea to save your settings, to be able to use them in other simulations. For this, just save the analyzer file. And now, we need to take a very important step, namely to balance the MZI. Does anyone know how we can change the schematic to achieve this goal? As we can see, the modulator length is 1000 micrometers, and as the comment in the module nicely informs us, there are 2 additional interconnection sections with the total length of 150 micrometers. As we are aware that the total length is 1150 micrometers, let's use that knowledge to set the length of the second MZI arm to the same value. Now we can run our schematic again. As our next step, we can now go to this panel over here and click Tile Horizontal. As a result, we can see 2 graphs containing the characteristic of the balanced and unbalanced Mach-Zehnder interferometer. Let's right-click on our trace and copy and paste it to the other window. It goes without saying that we can use the common Windows shortcuts Ctrl+C and Ctrl+V. Congratulations! Our first circuit is done. It wasn't that difficult, was it? I'm a big fan of the nice and easy approach of building schematics. Did I overlook anything? Oh yes, of course! Let's discuss our optical source now. As we can see, our building block named func_impulse_opt has the default value of peak power. In the frequency domain, that corresponds to a flat 1 mW power response for the whole simulation bandwidth. The azimuth parameter corresponds to input polarization. 0 value means TE polarization. 90 would be TM polarization. Let's set it to 45 degrees, which corresponds to an equal split between TE and TM polarization. With this setting, let's visualize the phase, group delays and dispersion of the output signal. And of course, at this point we run our schematic again. We are going to play with the analyzer a little bit. If you go to View, Control Panel, OSA Settings, you will notice that the OSA plot section is locked. No biggie. We will be alright. All we need to do is to use a polarization filter. To visualize different polarization, we can switch between different polarization filters. Just go to Common Settings and in the section Polarization Filter, choose the filter types X, Y. X polarization corresponds to TE and Y to TM polarization. Let's choose X polarization. Now all is well. The section OSA plots looks promising and we can visualize the phase, group delays and dispersion. I'm happy to tell you that we are done with the first part. We've designed our circuit and we've learned some useful things about the test bench elements. And now, after this beautiful introduction, the real game starts. We are going to create some parameter sweeps and to optimize our structure. Sounds complicated? Not in VPI Design Suite. We are going to add a few more building blocks to visualize the output power of our circuit. For example, we can add the fork2 module to split our signal, the power meter module to measure the output power, the numerical analyzer 2D module to visualize it, and to crown it all, the cons module to refer to our swept parameter. Let's create a schematic parameter corresponding to the control voltage parameter of the electro-optic modulator. As we know, it is an important parameter that defines the behavior of the Mach-Zehnder modulator. We can visualize it as well. Give me 2 more minutes. We are actually nearing the end of our sweep and optimization game. We are going to open the global parameter window and create a sweep control. The simulation range is going to be from 0 to 35 and the number of points is 36. Tile the group vertically to see the results. Notice that on the bottom of the VPIphotonics Analyzer window you can choose the run number. This allows us to investigate the signal after each step of the sweep. There are also visualization options for stitching, superimposing and averaging our signal. This is exciting, isn't it? Are you still with me? I promise it won't take long now. We are almost there. The main revelation is coming soon. We have done a parameter sweep. Let's make an optimization now. As a final twist, we need to add a post-value module that will be sending the signal information to our optimization sweep. All we need to do now is to repeat the procedure to create a sweep control on the control voltage parameter. This time we want to change the mode option to optimization, objective to minimize, and output to post value. And finally, run the schematic again. Now we can copy our optimized graph to the sweep and see its optimized value. If you are like me, you love obtaining optimized values. They do make our life so much easier. What is also important here is that after optimization we can apply the optimized value in one click. We just did it! I'm happy to tell you that our first optimized circuit is ready. In my next videos, we will take a look on some other useful things. I'll be showing you how to create a hierarchical design using the so-called regular galaxies, how to add galaxy parameters, and how to use mathematical and Python expressions as well as initialization scripts in parameter settings. I hope this is enough reasons to stay tuned. It will be well worth your time. If you enjoyed the video, we would be happy to receive your feedback. If you would like to learn more about our software and products, please visit our website at VPIphotonics.com.